Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Chris Jackson. We're going to talk about what fault tree analysis is for those who haven't heard of this before, perhaps those who have, but wouldn't mind a little refresher.
Well, I've heard of it. I've never used it. I know the concept. I've, probably used it very poorly with the team once. The task was, what do we tell the customer service folks is likely to fail? And we had Pareto's and a bunch of other stuff. And somebody in the group said, let's send them a fault tree analysis. I think I know what that is. And we use it as a brainstorming framework. Here's the top thing, customer complains it's failed. And then what could it be? And it quickly expanded. And so it kind of kept it as failure modes. I don't think we actually used the fault tree part properly.
Well, I mean, there's two different ways fault trees can be used, two main different ways, I should say. And one is to model system reliability. You can use fault trees because they're based on logic. They have logical gates, the AND gate, the OR gate, great for modeling things like series systems where the system fails if any component fails. So you have an OR gate when you essentially say, which essentially tells you that your system will fail if component A fails, or component B fails, or component C fails, and so on. And then you have the AND gate, where essentially all input events need to occur for a fault to propagate up, which essentially then allows you to model a system which has redundancy. So that's a system with redundancy will only fail once all components fail. So the parallel system will fail if component A fails, and component B fails, and component C fails, and so on. So AND gates are great for redundancy, and OR gates are great for modeling series system reliability with no redundancy. But you were talking about sort of the brainstorming approach too, where fault trees can be great for essentially structuring our brainstorm about what went wrong with something. And I think the three big visualization tools, or three big tools in RCA when it comes to root cause analysis, are the 5 whys,
Yep.
Ishikawa diagrams, or the fishbone diagrams, of course, and effect diagrams, and fault trees. And 5 whys is useful for observational logic. That is, you ask yourself, why did this happen? Okay, why did that happen? Or this, why did this happen? But it only works if you're, for example, in a manufacturing plant or facility, and it can visually answer the question through observation. 5 whys is terrible if you don't have the ability to observe the answer, because you ask 10 different people to do 5 whys, you get 10 different root causes of failure, if that's to speculate. And that's where deductive logic for root cause analysis then becomes very helpful, where you brainstorm and speculate what could have gone wrong, but you need a more comprehensive visualization methodology into Ishikawa diagrams and fault trees, which are both pretty powerful, sort of recording or structuring in a visual way the brainstorming session behind more detailed root cause analysis.
Yeah. Now, I find, all 3 tools are great when you got more than one person working on it.
Right.
But even fault tree on your own is, I still think they really are team activities, because I don't think any one person knows all the ways that a bearing can fail, for example. Because you need knowledge of how people use it, what could go wrong in maintenance, what could go wrong in installation, what could go wrong in manufacturing, what could go wrong with the design process, and on and on and on. And very few people have all of that intimate knowledge of how anything could lead to a failure. So I tend to think of all these tools as group activities. I've also seen fault tree being done as a guide to failure analysis. It's done as a preempt, kind of setting up, what do we need to do maintenance on? Where are the single point failures we need to have spares available for? What kind of used in following the design process afterwards than all the other activities we need to do during its life cycle.
Yeah, I think what I don't know if you're talking about this, but fault trees are great for troubleshooting guides. So you need to speculate what customers might experience, like when they have your device.
Yeah, it doesn't turn on. This is my favorite.
Right. And so you might need to create your own fault tree to go through all the scenarios to come up with the troubleshooting advice for that.
Well, that's where the top event would be with the customer would report, doesn't turn on, it doesn't calculate correctly, the mouse is frozen or whatever.
Mm-hmm.
And then I think then at that point, then the probability of this cause versus that cause then becomes, is it plugged in? Is it, what are the first questions you ask? What are the diagnostics you do to troubleshoot it? And you can go down a prioritized list if you've done a proper fault tree, is what's most likely to occur. I see an advantage in that.
Absolutely. And fault trees, when used in that way, will help you identify potential root causes or reasons behind issues and failures. They won't of themselves give you a prioritized list based on likelihood. That's where expert and engineering judgment comes into play. But they give you a list. And when you do it well, when you brainstorm in the group the way you're talking about, in one layer at a time, you almost always get fantastic results. The approach I use is I give people big sticky notes or post-it notes. And when I ask a question for brainstorming, go one layer down, I say, okay, I want you to write down 3 potential answers to this question or 3 potential reasons why this event occurred. Get people to write down 3, I said, well, minimum of 3, which means you don't have groupthink and you sort of circumvent a lot of other psychological issues when you're having group discussions. And tell you what, the coverage of ideas is, if you have a good team, a diverse team, motivated team, boy, you get some good answers and some really good results.
Now, I'm going to go back to one of the, maybe it was just because of the software. It wanted to say, well, what's the probability of this component failing? And then the and OR gates then, and maybe it's just the books, it's probably why I avoid using fault trees in general, is that you needed all this information and then you could run up the calculations of what's the probability of this top event occurring from all of its potential causes. That's a lot of detail for even a simple system. But there's a mathematical element to fault trees, from what I understand.
But that's for system reliability modeling. Like I think I mentioned at the start, the two main reasons you use fault trees are to do system reliability analysis, which is very quantitative, which is where those component failure probabilities become very important.
Mm-hmm.
And then there's the sort of the brainstorming sort of structure gives brainstorming sessions, which is invaluable. Very different purposes, very different reasons for doing fault tree analysis. And software can't tell the difference. You need to tell the difference.
I get that. In context and meaning, it might be all I need to do to say, we need to fix this, this, and this to improve the system or to identify the root cause of this particular issue. Gives us clues to work off of. And engineering judgment comes into play. Yet that same model we created in the brainstorm, if we populate it out, it might become a valuable system model.
Could be, yes.
For the reliability of it.
It's not always, the case, because, for example, if you conduct a root cause analysis on why a smart lock failed, for example, and one of the root causes was you used, or didn't have rubber dampening mounts for the PCB. If you design that out of your system, then by putting rubber dampening mounts in for your PCB, your printable circuit board, well, that basic event no longer exists anymore. So the idea is root cause analysis, fault trees or Ishikawa diagrams. You're trying to address the root causes that are found. And then if you have whatever's left, everything's going to fail. So it doesn't, you're never going to eliminate every single root cause of failure. It just means that you know when it does fail, how it will fail, and they're the ones you can more easily model. But yes, you can convert it, but what you don't want to do is use the exact root cause analysis fault tree during brainstorming, because hopefully you've addressed a good number of those root causes. They're no longer relevant or applicable.
Yeah. Well, that's one part I've run into, and it's the same issue I see many teams struggle with FMEA. It's a living document, especially during development, is that it's a tool for you to prioritize, to look for opportunities, to look for, serious flaws in the thinking of the design or the process. All of those things help improve the design as you go through it. FMEA and fault tree, I see both can do that if it's not one and done. Doing a fault tree and checking it off the list has little to no value whatsoever. You might get paid for doing the fault tree in some contract terms of some sort, but if you don't actually use it, you're kind of missing the point of why it was even in the contract, in my opinion.
Yeah, concur. It's all about, I've seen fantastic, well, I won't say fantastic, but I've seen reams of paper in a FMEA report, for example. Since you might know where I'm going with this, and it was completely useless when all was said and done. It's all about, I suppose, coming back to the main reason you do any sort of reliability engineering activity is, well, what's the decision you're going to inform?
It took us long enough. It took us almost 12 minutes to get to what's the decision we're dealing with.
That's right. Are you trying to measure reliability or trying to improve reliability? So if you're trying to measure reliability, system reliability modeling might be the way to go. If you're trying to improve it, then RCA might be the way to go, which will give you a completely different fault trees. Of course, if you're just trying to satisfy a clause in a contract, well, get off this podcast.
well, rethink what you're doing and see where you can actually make it actually add value to you and your customers and your industry and stuff like that. And one of the things I run into, is completely off topic, is the regulatory testing, so you get the little stamp on the side. I'm thinking of like UL on something you have to plug in. There's reasons for it. And it's legislated or it's legal. Sometimes it's a regulatory requirement by law. Other times it's a condition to be on that market in general. But those tests have to be done. And I always look at those as, well, those are perfectly good prototypes or products we're doing over there. How much other information can we get out of it? So I go back to FMEAs and fault trees and going, given those stresses, what do we expect? And are we surprised or not surprised? Are we learning different things? Is our understanding of how this product is likely to fail, did we miss something? And the first time I ran into it, somebody said the regulatory test failed because we had too much electromagnetic interference, EMI. Is that what that stands for? Emissions. We had too much radiated energy coming off our system. And so we failed this regulatory requirement for how much energy, how much radiation comes off of it. Not nuclear radiation, but electromagnetic radiation that would interfere with other devices nearby, potentially. And that wasn't in our thinking about how this product could fail, is the regulatory failures. And we completely missed that. And we were thinking about, this cable doesn't connect, or this is intermittent, or this thing, solder joint fails, or whatever. We did a lot of that stuff. And like, we said, and then there's a long discussion. Is that a failure if we can't put it on the shelf at the store? Product's working just as it's supposed to. Yeah, is that a failure? So I find, what are the boundaries to what's your fault tree, or even FMEA? What are the boundaries? And does it include things like regulatory or, other sets of requirements that are imposed on the product for one reason or another?
Yeah, good old what is a failure discussion.
It's a subject for another whole 2-day episode.
But going back to what fault trees are, I suppose we've said what they can be used for. They are very powerful tools. They're not always the right tool, because again, it depends on your decision, but they're a logic diagram. They start with the top events, so some sort of a weirdly rounded shape at the top, which represents something undesirable, like system failure or customer returns or not hitting enough, making enough profit, or solder joint fracture, whatever it is, with a cascading bunch of shapes branching out beneath. Like in my fault tree analysis courses, I sort of say it's not so much a fault tree, it's more a fault root system, because we associate trees as having a trunk which branch upwards and outwards, whereas fault trees are realistically a single event that branches downwards and outwards.
Well, you should draw it upside down, then it's, then it's branching.
That's true. But they're really good at visualizing, logical relationships between causes and effects. They're not really good at dynamic stuff. There are dynamic fault trees out there, but I won't go as far as saying it's putting a square peg in a round hole. But fault trees are designed to really deal with logic that doesn't change. And what that means is that if failure occurs, if one component fails before the other one, but not the other way around, then that can be challenging to model in traditional fault trees. Not impossible, and you can get quite good at it, but event trees, for example, are much better at looking at accident scenarios where human decision making takes us one way versus the other.
Mm-hmm.
A nuclear power plant, for example, it doesn't matter if the human operators make the right or the wrong call. 3 Mile Island, for example, and that wouldn't have happened if the operators did nothing after the issue.
They ended up making it worse.
Yeah, made it much worse.
Well, there's also, I think, interdependencies. If one piece is not failed, but it's running hot and it affects the performance of some other part of your system, that then leads to failure. There's a dependence there. And as things age, they change their properties and change their ability to withstand the stresses and so on. And I hate to, you don't want to dive into that unless you need to. And it again goes back to what decision you're working on. Yet it's way too easy to put in fixed estimates and as designed kind of thing. In critical systems, you certainly need to look at, well, how does that radiation affect the elements within their system? How does repeated use or start and stop systems, how does that affect the system over time? It's going to change the probabilities of things failing. I remember years and years ago, it wasn't exactly a fault tree, but it was this guy. He was the chief of the failure analysis lab in our building. Back in the day when I actually had a failure analysis lab with all this cool equipment down there we could take stuff apart with. He said, ideally we would put all of the components and all of our design interfaces on a big long list, and then we'd understand the strength of each and every one of those elements. And then we'd understand the attendant stresses that are applied to it. And so we'd have all these, a couple thousand plus stress strength curves. And then at the end of the day, we'd look at the ones that overlap and go try to do something about those. I says, well, that sounds easy. And he goes, that the stresses change. Customers use our products in different places that we didn't anticipate, or as they age, the strength changes. And so, so think of these things as two, bell-shaped curves that are moving. And unless you understand how fast and how quickly each of those things move, we only have a snapshot of what's going on. Now, we don't do that because it would be a huge effort to come up with all of those curves for even a simple system. Yet that thought process is what we're really after, is what is most at risk now and what's most at risk later as these things age. And so when I look at fault tree, it's a snapshot right now. And then if you're looking at it as, well, will our product last 10 years? Well, what part of these blocks, what part of these systems, what part of these components will behave differently 10 years from now than they do today? And I think that's a wrinkle in fault trees and again, back to that, what's the top question? What are we trying to focus on? Because a system model with, package failure rates on the side of the container that we got the components in gives us a starting point, but it's not the full picture.
No, and there are times where you might not want to use fault trees as well. I mean, the natural competitor to fault trees when it comes to system reliability modeling are reliability block diagrams, and their strength is that they can more easily mimic the physical layout of a system, which a lot of people would obviously find appealing. They are much harder to manually analyze. That's becoming less and less of an issue these days. But you cannot, if you wanted to get to the bottom of system reliability analysis using fault trees, it's much easier if you have to follow the logic of a fault tree. So fault trees are all about logic, and reliability block diagrams can be seen as all about visual mimicry. Visual mimicry is great for us trying to understand a system. Logic's great if we're trying to quantitatively analyze a system. So it depends what you're trying to do. But when it comes to root cause analysis, the other natural competitor for fault trees is the Ishikawa diagrams, which are fantastic. Ishikawa diagrams and fault trees are both great deductive logic tools. 5 ways is observational logic. Ishikawa diagrams and fault trees are deductive logic. And I often tell my clients that when they say, well, which one should I use? Say, well, which one do you like better? Which one do you feel more comfortable with? Their pros and cons are fairly similar. Ishikawa diagrams can't represent complicated logic. It just represents a cause and effect. Whereas if you do root cause analysis with fault trees, you can, especially in software, RCA, talk about, look at this has to happen first before this particular effect would occur.
Sequence of events type stuff.
Yeah. So that's the main difference. I also find that you often, when you're doing root cause analysis, what you start off with on your whiteboard gets pretty crowded pretty quickly. I do find fault trees easier when I do, like when I facilitate, I use big sticky notes on a whiteboard. I find that easy to move around than redraw an Ishikawa diagram, but I'm sort of being finicky here.
Well, it's one of these things that I know that you've got to have spent some time on, and recently published a course on fault tree analysis. Does this cover all these different uses, or is it?
Absolutely, yeah. So one of my issues, yeah. So my fault tree analysis course, which by the time this podcast comes out, is it either has been launched or is going to be launched very, very shortly. One of my complaints with previous fault tree analysis courses or teachings was that it was the concept of the instructor that dominated the flavor of the fault tree analysis course. So, for example, if the instructor or the teacher had only experienced fault trees and root cause analysis, they only taught fault trees as if they could be used for root cause analysis, and vice versa. When I had people who were instructors who would only ever use it for system reliability modeling, well, they only got taught as if fault trees could be used for system reliability modeling. And so I find that's, an enduring issue that we have in our industry, is that people just associate fault trees with one or the other, and hard to be convinced otherwise. So my fault tree analysis course is all about making sure that everyone is super confident with fault trees for whatever application they need to use it for, be it system reliability modeling or root cause analysis, or other things as well, like working out what features you need to have in your design in your system. So yeah, those 28 short 15-minute lessons cover the whole gamut of becoming a fault tree master with precious few equations and lots of illustrations and stuff.
I don't know if that's a selling point or not, but you do get the concept across versus just a plug and chug without much understanding. I appreciate that when you put your courses together. So anyway, if you're listening to this and we've whet your appetite to understand fault trees or you're using those in some other way that we hadn't talked about, let us know. If you're interested in Chris's course, we'll probably, we should have a link to it underneath this, or we can update it, but you'll find it on undesirable.com. And I think, Chris, it'll be on your site also at cutis.com, right? Am I pronouncing that right?
I call it Acuitas.
Acuitas, okay.
It's
Acuitas.com.
Yeah, I've often debated whether I should have a more naturally phonetic name, but I think we have enough back and forth on accendo versus accendo versus. Yeah, it's
as long as you can find it. It's not, smith.com or something like that.
Right.
But, so it goes. But anyway, take a look at the course. It's highly recommended and all that good stuff. Chris's teaching style and the way he explains stuff. So that's all the good stuff. So this was a blatant end of this topic. We thought, we got to talk about fault trees. But it's hopefully not too much of a distraction. But it is something to get a handle on and to use it in your toolbox and get the value out of it. But if you've got some questions about it or good stories about what worked or didn't work for you, let us know. Head over to ascendoreliability.com/go/SOR. Chris and I are available through LinkedIn, and the other hosts too are available through LinkedIn and our About pages. So plenty of ways for you to get in touch. If you're really not interested in fault trees, well, what are you interested in? Let us know. We'll look forward to your comments and questions, and look forward to your attending or listening to our future podcast. So with that, Chris, I think we'll wrap this one up.
Well, Fred, always a pleasure and always good to talk about fault trees.
I know. All right. Thanks, Chris. Talk to you later.
See you, Fred.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.